All right, recording is rolling. I see you guys did this version lab. You guys put these lab weights on your desk, tilt your desk until it slides down your desk at constant velocity. You guys were using this protractor to record this angle. Now, I'm going to just make up some data here. Let's say I just copy paste the same weights as I had before. Right? And what angle did it slide down at constant velocity? I'm just going to make up some numbers. Let's say it's like 16 degrees, 17 degrees, 18 degrees, 17 degrees, 18 degrees, I don't know, something like that. That might be in the ballpark of about what you guys saw too, plus or minus a few degrees. Okay. I told you guys to take the tangent of the angle, and I didn't say why, but let's just follow the directions, play it out, see what happens. What's tangent of 16 degrees? That's like 0.29. Tangent of 17 degrees, like 0.31, which also goes right here. How about tangent of 18 degrees? It's like 0.32. All right, what is 29, 31, 32, 31, 32, all divided by 5? All right, 0.31 it averages out to for me. Okay, guys see that? Okay. So I found the angle for each of those lab weights, right? So wildly different lab weights. It's about the same angle over and over. Therefore, the tangent angle is also about the same. Took the average, got it over there. This graph says tangent of the angle versus the weight. So that means tangent of the angle is going to go on the vertical axis, and the weight in newtons goes on the horizontal axis. Now, tangent of an angle is a unitless ratio, right? Not very often do you see unitless numbers in this class, but this is an example of that. Weight is in newtons. I forgot the same weights before, so let me go ahead and scale it the same as before. 0, 2, 4, 6, 8, 10. Okay, just like before with the first version of lab. Okay? Tangent of the angle, let's go 0, 0.1, 0.2, 0.3. Okay, that little space above that. Okay, so that should contain all my data. All right, let's plot these as Cartesian coordinates. So for the half Newton weight, it was 0.29. That's bam, right about there. For the 1 Newton weight, it's like 0.31. Bam, right about there. 2 Newton weight, 0.32. Bam, right about there. 5 Newton weight, 0.31. Bam, right about there. And the 10 Newton weight was like 0.32. Bam, right about there. So somewhere thereabouts, right? But if it was the same angle pretty much over and over, pretty close to, and therefore the tangent of that angle was also pretty close to the same, isn't this just going to be a flat line? Like flat line? Zip. Just like that, right? Oh, a couple of questions down here in these boxes. Tan theta equals, okay, so we're setting up an equation. It doesn't say y equals, but it's the exact same concept. It says tan theta equals. Tan theta is your y-axis. So, guys, what's the equation of just a flat line like that? So it has zero slope. So isn't it just whatever value it is? Which for me, it was like this number right here, 0.31, right? It's not 0.31 times anything because it's just 0.31. It looks pretty well universally, regardless of what the weight is. See how there's no relationship between those two variables? There's no relationship between like the angle or the tangent of the angle and the and the weight itself. There's no relationship between those two. Hey, do you guys remember? Here. Guys, remember this right here? It looks like this, just like y equals k, right? No relationship. You guys remember no relationship? Okay, let's go right here. Okay, so how does the follow-up question? How does tan theta relate to the coefficient of kinetic friction from the first side? Oh, look at that. It's like the same number. Right now, maybe your numbers didn't work out exactly as clean, but it should be kind of in the same ballpark. These two shouldn't be too far away from each other. They should be pretty close, right? Because tan theta should represent the coefficient of kinetic friction, right? So now that's from an empirical point of view. Let me go back to this proof that I had started, but then I covered part of it up, right, and then I stopped the video. Right? So we're looking at the block sliding down at constant velocity. That means equilibrium. Right? We got to this point where we're saying, well, this mg sine theta balances out with the friction force, so we get there. Right? The next step was to say, well, I remember from before that friction force is coefficient of friction times normal force. So I can make that substitution right there. Bam. Right? normal force is equivalent to mg cosine theta. Take that substitution, bam. Right? And guys, at this point, what cancels out on both sides? mg. So the lab mass doesn't matter. And for that matter, you could hop planets. And like if you took this whole system to Mars, it should also like slide down at the same angle, right? Because the gravity field doesn't matter. If you're solving for coefficient of friction, that's what this is right here, coefficient of kinetic friction. Is what is sine divided by cosine? Tangent of the angle, which is exactly what I was showing you right here. The fact that these numbers are probably pretty dang close to the same number, right? The tangent of the angle that slides down at constant velocity represents the coefficient of friction, right, for that scenario. All right, so like I told you at the beginning of class, go ahead and hold on to this lab paper because on the other side is printed a different lab. Ooh, it's like a 2-part Atwood lab. And that's going to be probably tomorrow's adventure. And that is a wrap on today.